This is Lecture 1 for Module 12 in the book Problem-Solving Guide for Mechanics and Thermodynamics, understanding the internal energy, the thermal energy transferred into or out of the gas by heating or cooling, and the work done by or on the gas. Of course, you're not going to gain mastery of these concepts unless you do a lot of problems. I recommend doing a lot of problems after and perhaps even during the video. Pause the video several times and think. It's a great exercise for your mind. So I'm going to talk about understanding rather than remembering. So we have a monatomic ideal gas confined to the left half of a container. That's helium. The right side is a vacuum. What we're going to do is going to remove the partition by lifting it up. Like that. We just take the partition up and the helium goes and now occupies the entire volume. The volume of the gas here is twice what it is here. What happens to the temperature of the gas? Think about what's going on at the level of the atoms. Now, consider the same initial situation, but there's a piston there. And we pull the piston back until the volume of the gas doubles. There's a number of rules you can remember about free expansions, isothermal expansions, isobaric expansions, adiabatic expansions. But if you're just remembering rules without understanding, you're going to forget them all. So the question is the temperature of the gas the same in these two situations? If you understand fundamentally what's going on, it will be obvious to you. If you remember rules, you will have no idea if you don't remember the rules. So understanding the concepts is key to doing well in this module. So here's a sample problem that we're going to be able to do once we get done. 15,000 joules of thermal energy, that's Q, are added to a monatomic ideal gas by heating it. 15,000 joules of thermal energy go into the gas because we have a Bunsen burner underneath it. As a result, the gas does 10,000 joules of work by expanding, pushes the piston up. What's the change in internal energy of the gas? Okay, ready to start the lecture. The first step we already did is to understand these three terms: the internal energy of the gas, the work done by the gas, and the thermal energy transferred into the gas. Both W and Q can be positive or negative, and of course the internal energy of the gas can go up or down. The internal energy is just the sum of the kinetic energy of all the atoms in the gas. If the molecules are complicated, they can have vibrational and rotational states as well. We're going to focus only on ideal monatomic gases here. So if you have 5 moles of helium at 300 kelvins, the internal energy is independent of the pressure it exerts. It's also independent of the volume of the container confining it. It's just 3/2 nRT. N is the number of moles, or atoms, depending on what the units of the gas constant are, and T is the absolute temperature. So if you have a given number of moles, its internal energy is a linear function of the absolute temperature. So here we're going to consider 2 ways to change the temperature. One is by heating or cooling it. That's pretty obvious. We can put it in an ice bath to cool it. We can have a Bunsen burner to heat it, or whatever. We can also expand it or compress it. These two are fundamentally very similar at the atomic level. They're very similar. In both cases, the atoms of the gas are being hit by atoms that have a different kinetic energy. In the case of heating the gas, what you do is you heat the container, and then the gas atoms get kicked because the atoms in the walls of the container have a high kinetic energy. So they give that kinetic energy to the gas atoms when they collide. When you compress the gas, you're also hitting the gas atoms with something that has a higher kinetic energy, because when the piston moves in, it kicks the atoms and they speed up. And if the gas is expanded, the piston is receding, the atoms are going to rebound, with a smaller speed. It's just mechanics. If you throw a ball against a wall that's moving back away from you, it's going to rebound with a slower speed. If the wall's coming in, it's going to rebound with a higher speed. When the gas is expanded, we say the gas does work. If the process is adiabatic, in other words, we wrap some insulation around it so we don't allow any heat to flow into or out of it, the gas will cool down when it's expanded, and it's going to heat up when it's compressed. And you should understand why. You shouldn't be remembering that rule. So now let's think about some problems in thermodynamics. A gas does 10,000 joules of work while 15,000 joules is transferred to it by heating. What is the change in internal energy of the gas? Do not think about what's the equation for that. Think about what's going on, and think about understanding the concepts. Humans think, computers calculate. So let's go back to this problem. Is the gas expanding? The gas is doing 10,000 joules of work, so the gas is expanding. When the gas is expanding, it loses kinetic energy when it hits the receding wall. So the gas lost 10,000 joules of internal energy by colliding with the receding wall. That's what we mean when we say the gas does 10,000 joules of work. But we dumped in 15,000 joules by heating it. We made a deposit of 15,000 joules into it with our Bunsen burner. So the change in internal energy must be plus 5,000 joules. It should make sense. If it doesn't make sense now, we have to do more problems. Here's another one. A gas is compressed until 20,000 joules of work is done on it, and 15,000 joules are removed by cooling it. What is the change in internal energy of the gas? The gas hits the incoming atoms. The piston hits the atoms, and they're kicked, and they gain kinetic energy, and they gained 20,000 joules. The piston made a deposit of 20,000 joules into the internal energy of the gas by hitting it. But 15,000 joules was removed by cooling it. Net change is plus 5,000 joules of internal energy, right? Should make sense. Let's think about the equation. The internal energy, the change in internal energy, is Q minus W. When the gas does work, the internal energy drops. When you put thermal energy into the gas, the internal energy goes up. W is the work done by the gas. When we do problems, we talk about work done by the gas, work done on the gas, but the variable W is always the work done by the gas. So W can be positive or negative. If the gas does positive work, it's pushing in the direction the piston is moving. Work is force times distance. If it's moving in the same direction, if it's pushing in the same direction it's moving, that's positive work. Don't focus on remembering the rules, understand the concepts, and you'll never have to remember anything. You should never say, I can never remember what the rule is for. It's easy to forget rules if you don't understand the concepts. Here's another one. 25,000 joules are added to an ideal monatomic gas, and its internal energy goes up by 15,000 joules. Did its volume increase or decrease? Is the work done by the gas W positive or negative? And what is the work done by the gas? 25,000 joules are added. That's Q. Make it the positive 25,000 joules by heating it. But its internal energy only goes up by 15,000 joules. We're missing 10,000 joules. The gas must have done work by expanding. The piston must have went up, and that's how it lost energy. So the volume increased. The work done is positive. And we can calculate the work done. It's plus 10,000 joules. So you have a deposit of 10,000 joules. Only 15,000 joules was gained. The gas must have lost 10,000 joules of energy by colliding with the receding piston. So the volume went up. The work done by the gas is positive. The work done is plus 10,000 joules. So there's the equation. If you want, just plug it in. It works. 15,000 equals 25,000 minus the work done, which is positive. A good analogy is a bank account. The internal energy is the balance. Q and W either make deposits or withdrawals. It is a good idea to think about whether each Q and W is making a deposit into the internal energy of the gas or a withdrawal from the internal energy of the gas. Don't trust the equation to give you the right positive or negative sign. Just think about it. So here's another one. A monatomic ideal gas is expanded until it does 12,500 joules of work and 7,500 joules are removed from the gas by cooling it. What is the change in internal energy of the gas? If you thought it's got to be minus 20,000, then you're well on your way to understanding the concepts and becoming a master. So both Q and W are making withdrawals. The thermal energy removed by cooling is minus 7,500. The work done by the gas as a result of colliding with the receding piston causes the gas to lose another 12,500 joules. So the work done by the gas is 12,500 joules. 7,500 was removed. So now let's relate the work done to the change in volume. We're going to be quantitative. So let's consider a gas in a cylinder with a movable piston. The atoms are hitting the walls and the piston. If the force is constant, the general equation for work done is force times distance. The force and the distance are in the same direction or in the opposite direction here. If they're in the opposite direction, you're going to put a negative sign in. F is the force the gas exerts on the piston. So let's assume this piston has a cross-sectional area A and is displaced by D. It moves up or down a distance D. The change in volume is just A times D. The area of the piston times the distance it moves. So we can substitute this into the work expression for D. D is delta V over A. And now we have the work done is P delta V. That's only if the force is constant. So for constant pressure, the work is P delta V. So the work done by a gas at constant pressure is P delta V. If the pressure is not constant, you have to use the general equation, integral of F dot dx. So you have to integrate P dV. If the pressure is constant, you can pull it out of the integral, and the integral of dV is just delta V. But sometimes the pressure is a function of volume. So if this is the function, if it's isothermal, we can pull the temperature out. So now we have to integrate dV over V, and that's natural log of V. At constant pressure, though, the work done is P delta V. If the volume increases, delta V is positive. The work done by the gas is positive. The gas is pushing in the direction the piston is moving. The atoms of the gas lose kinetic energy when colliding with the receding piston. So as a result of the expansion, the internal energy of the gas drops by P delta V. The work done is P delta V. That's why it has a minus sign in the internal energy equation. Then we add in the Q. Now we can get the total change in internal energy of the gas. So here's the sample problem we started with. 15,000 joules of thermal energy are added to a monatomic ideal gas by heating it. As a result, the gas does 10,000 joules of work by expanding. What is the change in internal energy of the gas? You shouldn't need an equation for that. It's plus 5,000 joules. Now let's go back to this. So here's a helium atom bouncing around, hitting the wall, bouncing the wall, and then all of a sudden the wall's not there. The partition was removed. Why would the molecule speed up or slow down? It just keeps going. The temperature's the same here. How could it possibly change? What is speeding up the molecules or slowing them down? Here the piston's moving back, and every time the helium atom hits the piston, it rebounds with a slower speed. So this cools off in this situation. This situation, the temperature stays the same. There's probably a rule for that. I have no idea what it is. That's lecture 1.